The internet is a funny place filled with creativity, wild speculation, and sometimes outright panic. Every day, new stories and rumors pop up, some hilarious, some bizarre, and a few that make you wonder if reality itself is starting to unravel. Recently, a wild rumor spread like wildfire online that Fermilab scientists had accidentally torn a hole in reality. Social media posts, memes, and even some news outlets picked up the story, fueling a frenzy of speculation and concern. Imagine, for a moment, a wound in space-time, an actual rift, opening up in a laboratory just outside Chicago. The idea sounds like something straight out of a science fiction blockbuster, complete with swirling portals and alternate dimensions. The story, packed with jargon about quantum entanglement and mysterious experiments, quickly evolved into a full-blown conspiracy theory. People began to wonder, could scientists really break the universe? Did Fermilab accidentally break the universe? It's a question that captures the imagination, blending our fascination with the unknown and our fear of what we don't understand. But as with many extraordinary claims, there's often a tiny seed of truth at the center, one that gets twisted, exaggerated, and misunderstood as it spreads. In this case, the seed was a fascinating experiment at Fermilab, but it had nothing to do with cosmic destruction or reality-bending disasters. The real science was far more nuanced, and, in its own way, even more intriguing. To understand what really happened, we need to look at a scientific paper published in 2022. This paper described a complex experiment, but its findings were quickly misinterpreted by those outside the scientific community. The story of Fermilab supposedly breaking reality is a perfect example of how science can be misinterpreted, especially when technical details are lost in translation. It highlights the gap between the complex world of physics and the way the public perceives scientific breakthroughs. Sometimes the truth gets buried under layers of confusion and sensationalism. So let's set the record straight and appreciate the real story behind the headlines at Fermilab. In this chapter, we'll separate fact from fiction, dig into the actual science, and discover what really happened in that famous experiment. Join us as we uncover the truth behind the rumors and explore how a real scientific discovery became the internet's latest tall tale. The cosmic rumor didn't start in a secret lab, hidden away from the world, or whispered among a select few. Instead, it burst into the open with a bold public announcement that sent ripples through the scientific community and beyond. The news was published in the prestigious journal Nature, a platform known for sharing some of the most significant scientific breakthroughs. This wasn't just another research paper, it was a statement that something extraordinary had happened. The experiment itself was the result of a remarkable collaboration, bringing together brilliant minds from Caltech, Google, Harvard, and Fermilab. These institutions pooled their expertise, resources, and creativity to tackle a challenge at the very edge of modern physics. At the heart of this effort was Google's Sycamore quantum processor. Unlike the massive particle colliders that smash atoms together, Sycamore is a marvel of miniaturization, operating at the quantum level with unprecedented precision. Sycamore's power comes from its qubits, tiny units that don't just follow the rules of classical physics, but instead behave according to the strange and counterintuitive laws of quantum mechanics. These qubits can exist in multiple states at once, enabling calculations that would be impossible for ordinary computers. The team set out to test a mind-bending idea from theoretical physics, one that had previously existed only in equations and thought experiments. Their goal was to see if a quantum computer could bring this abstract concept to life, at least in a simulated form. Experts from Google, Caltech, and Fermilab worked side by side, combining their knowledge of quantum computing, physics, and advanced mathematics. This was a true meeting of disciplines, with each group contributing a vital piece to the puzzle. Rather than building a physical object, their mission was to simulate a theoretical one, a task perfectly suited for a quantum computer. They programmed Sycamore to mimic the behavior of a system that, until now, had only existed in theory. Using Sycamore, the team managed to model a traversable wormhole, a shortcut through space-time that has fascinated scientists and science fiction fans alike. This was a landmark achievement, showing that quantum computers can tackle problems once thought impossible. It's important to understand that this simulation was like using a computer to model the weather. The results are powerful and informative, but they don't mean we've created a real wormhole, just a digital representation. Still, the experiment demonstrated the incredible potential of quantum simulation. With these tools, scientists can now explore some of the deepest mysteries of the universe, testing ideas that would be impossible to probe in the real world. But it's crucial to remember, a simulation, no matter how sophisticated, is not the same as reality. It's a model, a way to explore possibilities and make predictions, but not a substitute for the real thing. What the team created was a representation, not an actual physical event. The wormhole existed only in the language of mathematics and computer code. Now let's dive deeper into what the scientists actually achieved and why this experiment marks a turning point for quantum research. The team of researchers set out to tackle one of the most intriguing questions in modern physics. Could a quantum computer simulate the behavior of a wormhole, a theoretical tunnel through space-time? To do this, they used Google's Sycamore quantum processor, a cutting-edge machine at the forefront of quantum technology. Their goal was to create a digital experiment that would mimic the conditions described by advanced physics theories. The simulation was based on the Sachdev-Ye-Kitaev, or SIK model. This mathematical framework is famous for describing a traversable wormhole, a shortcut connecting two distant points in space-time, at least in theory. The researchers translated this complex model into a set of instructions that Sycamore could process. They engineered two entangled quantum systems on the chip which acted as the two mouths of the simulated wormhole. Entanglement is a uniquely quantum phenomenon where particles become linked so that the state of one instantly influences the other, no matter the distance. Into this setup, they inserted a qubit, a basic unit of quantum information. Remarkably, the qubits seemed to vanish from one system and reappear in the other, as if it had traveled through the wormhole. The data they collected matched the predictions for how a signal would behave if it actually passed through a wormhole, providing strong evidence that their simulation was accurate. This result was a major breakthrough, confirming that the theoretical model could be realized in a quantum computer. The team celebrated, knowing they had taken a significant step forward in experimental physics. The experiment demonstrated the incredible power of quantum computers to simulate and test ideas that were once purely theoretical, opening new doors for fundamental research. By doing this, the researchers created a bridge between quantum mechanics and general relativity, two foundational but often disconnected pillars of modern physics. However, it's important to clarify what actually happened. No physical tunnel or portal was created in the lab. There was no visible wormhole you could walk through. The wormhole existed only as a pattern of information within the Sycamore processor, a clever arrangement of quantum data, not a tangible object. The quantum information didn't physically travel from one place to another. Instead, it was reconstructed on the other side, thanks to the entanglement and the way the experiment was designed. In essence, what the scientists achieved was a kind of holographic projection, a mathematical and informational echo of a wormhole, not the real thing. With this in mind, let's now turn to the rumors and misconceptions that quickly spread after the experiment was announced. As the wormhole simulation news spread, the story mutated. Social media and forums shared unverified tales of strange occurrences near Fermilab. Stories of sensor glitches, energy spikes, and data blackouts emerged. These anecdotes felt authentic but lacked credible evidence. No official reports or verifiable data supported these claims. It was digital folklore, not scientific fact. In science, anecdotes aren't data. Extraordinary claims need extraordinary evidence. Fermilab operates transparently, with rigorous safety procedures. If genuine anomalies occurred, scientists would study them, not hide them. The idea of a global scientific cover-up is implausible. The scientific community thrives on discovery, not secrecy. These rumors persist due to fascination with the unknown and distrust of authority. Let's distinguish between a good story and the truth. While the internet buzzed with tales, Fermilab scientists focused on real work. Their research is vast and more fascinating than any conspiracy theory. Fermilab leads in understanding matter and energy's fundamental constituents. A key focus is neutrino physics, studying ghostly particles passing through us. Fermilab's DUNE project shoots neutrinos through Earth's crust to detectors. They study neutrino oscillations to answer big physics questions. Another puzzle involves the muon, a heavier electron cousin. The muon G2 experiment measures muon properties, hinting at new physics. Quantum simulation, sparking rumors, is crucial for understanding reality. Fermilab's mission is to piece together the cosmos one discovery at a time. To understand our experiment's power, look at the sky. The universe has natural particle accelerators, dwarfing human-made ones. Cosmic rays, high-energy particles, bombard Earth from violent cosmic events. Supernovae and black holes accelerate these particles to incredible energies. The Large Hadron Collider is powerful, but cosmic rays exceed it by millions. These particles have hit Earth for billions of years, a natural experiment. If high-energy collisions could tear space-time, the universe would show it. Yet the Earth remains intact, and the universe hums along. This cosmic perspective is a reality check. Our collider energies are significant but minuscule on a cosmic scale. Fermilab recreates natural phenomena safely, not venturing into unknowns. Nature is the ultimate safety inspector, and it approves our experiments. Beyond natural safety, simulations ensure Fermilab's work is safe. The Wormhole experiment was a digital exploration of extreme physics. No physical matter was at risk and space-time remained undisturbed. Simulation is a powerful, responsible scientific tool. Like engineers testing bridge designs, scientists simulate theories safely. Simulations explore extreme conditions like black holes or the Big Bang. Quantum computers like Sycamore model quantum rules in a virtual lab. This approach advances science boldly but safely. Physicists test outlandish ideas without physical risk. If a simulation fails, it's a chance to rethink, not a disaster. It's exploration by proxy, a journey of mind and algorithm. This method is fundamental to modern physics. Did Fermilab tear a hole in reality? No, they didn't. The story was a viral myth, transforming a scientific achievement. The truth is less alarming but more profound. Scientists used new tools to understand the universe's rules. Fermilab's work is about a quest for knowledge, not reckless experiments. They ask big questions about the universe's origins and laws. Fermilab searches for cracks in our understanding, leading to new theories. They opened a window into the quantum world, enriching our understanding. As we build powerful tools and ask bold questions, we'll replace fear with knowledge. Our universe remains unbroken, filled with endless wonder.